What if I told you the answer to "can machines think"
Yeah.
isn't quite what you expect?
And, well, the path to finding it involves this really clever game and a surprising shift in perspective that still shapes how we think about AI today. So, for our exploration, we're looking at a truly foundational text. I mean, this paper essentially kicked off the entire field of artificial intelligence.
That's right.
Alan Turing's groundbreaking 1950 paper, Computing Machinery and Intelligence. A listener shared this classic with us, and, right from the start, it poses this profound question. When we ask, can machines think? What are we actually asking?
Yeah, and that's exactly where Turing starts. He points out really insightfully that if you try to define machine and think using just everyday language, well, you quickly tumble down this philosophical rabbit hole
Right.
or end up with what he kind of dryly called an absurd statistical survey. Like asking people in a poll, it's just not a useful way to approach it scientifically.
So he needed a different angle. Exactly. He composes a completely different, much more practical question. And that sets the stage for what he famously calls the imitation game.
Okay, and that's really our mission today then, to properly understand this ingenious game, why it was so revolutionary back then, and how Turing used it so masterfully to anticipate and counter basically every major objection to machine intelligence.
Decades before it became reality.
Yeah, decades, even centuries before our current AI boom really took off. It's just remarkable how much of what he laid out still holds true.
It really is.
So let's unpack this imitation game. It's clearly much more than just some simple parlor trick, right?
Yeah.
How does it help us get around those, well, notoriously slippery definitions of machine and thinking that trip people up before him?
It's absolutely brilliant in its simplicity, really. The game, it involves three participants. You have a man, let's call him a woman, B, and an interrogator, C.
Okay.
Now, all three are in separate rooms. The interrogator, C, can only communicate with A and B through written messages. Think of like a teleprompter setup back then.
Right, text only.
Text only. And the interrogator's initial goal in the first version of the game is just to figure out which one is the man and which one is the woman.
Okay.
Now, the man, A, tries to mislead the interrogator, maybe tries to sound like a woman in his written answers, while the woman, B, tries to help the interrogator make the right call.
Standard sort of deception game.
Exactly. But here's the crucial twist. Turing says, okay, now let's replace the man, A, with a machine.
Ah.
The central question then completely changes. It becomes, will the interrogator be fooled as often by the machine as they would be by a human man trying to imitate a woman?
Right. Here's where it gets really fascinating, because this setup immediately sidesteps physical appearance, doesn't
Yes.
it? Even voice. It's not about whether a machine looks human or sounds human.
Precisely.
It just zeroes in purely on intellectual capacity, right?
Yeah.
The ability to respond and converse in a way that you just can't distinguish from a human mind. Is that the core idea?
That is absolutely the core brilliance. Turing, you see, completely sidesteps that impossible philosophical swamp about consciousness. Does it feel? Is it aware?
Which you could argue about forever.
Forever. Instead, he creates a testable behavioral definition of intelligence. It boils down to, can a machine act intelligently enough in this specific kind of linguistic interaction to fool a human? It's a pragmatic, functional shift.
And that still underpins how we evaluate AI, doesn't it? Like
Yeah.
large language models today.
Absolutely. Think about chatbots. It's still fundamentally about whether their responses are human-like. And Turing gave some vivid examples, too. He said, okay, the interrogator might ask for, say, a sonnet about the fourth bridge.
Okay, a creative task.
Right. And a human might honestly reply, count me out on this one. I never could write poetry, which is a very human response.
Yeah.
Or for an arithmetic problem, maybe a human pauses for 30 seconds before giving the right answer, or even makes a deliberate mistake to seem less machine-like. Even a complex chess problem could be posed. Maybe the answer comes back RR8 mate after a 15-second pause. The game allows for this whole spectrum of human intellectual activity.
But crucially excludes physical stuff.
Exactly. It carefully excludes only physical demonstrations. The witnesses in the game, they could brag about their strength or charm in their messages, but the interrogator can't ask them to, lift something or show their face.
It keeps it purely to the exchange of information.
Purely information.
So once Turing framed the question in this really clever behavioral way, the next logical step must have been, okay, fine, but what kind of machine are we actually talking about here?
Yeah.
Starts broad, but then narrows it down quite a bit, right?
He does. Initially, he sort of toyed with the idea of allowing any engineering technique anything goes.
Which could get weird fast.
Right. It led to these kind of absurd scenarios, like the philosophical puzzle of, could you grow a complete individual from a single skin cell? Which he explicitly says, no, that wouldn't count as a thinking machine for this purpose.
Okay, sensible boundary.
So he wisely restricts the machines involved to what he called digital computers. That was really the cutting-edge technology at the time, the focus of interest for anyone thinking about thinking machines.
And that definition only becomes a problem if they can't actually play the game well.
Precisely. If they fail the test, then maybe we need to reconsider the type of machine. But for starters, let's focus on digital computers.
And he breaks down what those are.
Yeah, he outlines the fundamental components. You've got the store, think of it like memory, or a human computer's paper holding data and instructions.
Got it.
Then the executive unit, which actually does the calculations, the basic operations. And finally, control, which is crucial. It makes sure instructions are followed correctly and in the right sequence. It manages the whole process.
So these machines, fundamentally, they're designed to mimic what a person does when they're just following rules.
Essentially, yes. They mimic the actions of what he called a human computer, basically. Someone meticulously following fixed rules written in a book, executing a program step by step.
And within this definition of digital computers, Turing introduces this concept that seems really profound, especially for 1950, this idea of universality. Can you unpack that? Why is that so important for machines trying to pass the imitation game?
Universality. Yes, this is a huge point. So digital computers are what we call discrete state machines, meaning they move in distinct steps or states. They jump from one definite configuration to another rather than changing continuously, like, say, an analog clock hand.
Okay. Discrete steps.
Right. Now, that might sound limiting, but the number of possible states, even for very early machines like the one at Manchester University he mentions, was already astronomically large.
How large?
He estimated something like 10 to the power of 50,000.
Wow. Okay, so complexity wasn't the issue.
Not in principle. It highlights the immense potential complexity these machines could handle. But the truly mind-bending part is this. Digital computers are, in theory, universal machines.
Universal?
Meaning that if you give any digital computer enough storage space, enough processing speed, and crucially, the right program, it can mimic the behavior of any other discrete state machine.
Any other one.
Any other one. So this beautifully simplifies the whole question. We don't need to ask about countless different types of potential thinking machines.
Right.
The question becomes, can one specific digital computer, if we program it cleverly enough and give it enough memory, play the imitation game successfully?
So one type of machine potentially could do it all.
In theory, yes. It means we don't need a bespoke machine for every single cognitive task. A general-purpose computer could potentially simulate any thinking process we can describe algorithmically.
That's a powerful concept. Now, even back then, 1950, when thinking machine was, well, pretty out there, people had strong feelings objection.
Oh, definitely.
And Turing, with amazing foresight, tackles several of these head-on. Let's start with a classic one, the theological argument. That feels like an obvious first hurdle.
It does, doesn't it? And this objection basically says, look, thinking is a function of the immortal soul, and God only gives souls to humans. End of story.
Machines can't have souls, therefore can't think.
That's the gist. But Turing, with his characteristic logic and maybe a bit of wit, pushes back. He questions the assumed limits on God's power. He asks, well, why would an all-powerful God not be free to grant a soul to an elephant, or indeed to a machine, if he chose to?
Turning the argument around.
Exactly. And he even draws this clever analogy to human procreation. He suggests that maybe building these machines could actually be seen as instruments of God's will, providing, in his words, mansions for the souls he creates.
Wow, that's quite a reframing.
It is. And he also points to history like Galileo's time, where religious texts were used to argue against new scientific ideas like the Earth revolving around the sun.
Which didn't end well for the objectors.
Precisely. His implication is clear. Theological arguments against scientific progress tend not to hold up over time.
It's a strong counter. Okay, but what about the more maybe intuitive arguments? The feeling that machines just can't do certain things like, be kind or have a sense of humor or fall in love or even just make a mistake. That feels very human, making mistakes.
Right, and that cluster of objections is what Turing calls the argument from various disabilities. Can machines do X, Y, or Z?
Yeah.
And he argues that many of these objections really come from what he calls scientific induction, based on our frankly, very limited experience with the simple machines of his day.
Like judging a supercomputer by an abacus.
Exactly. He's saying you're looking at machines with tiny storage capacities and concluding things about vastly more complex future machines. It's like judging an adult's potential based on what a baby can't do yet.
Makes sense.
And the machines can't make mistakes point is particularly interesting. Turing suggests, well, a machine playing the imitation game could deliberately introduce errors to seem more human, to confuse the interrogator.
Ah, strategic mistakes.
Exactly. He distinguishes between errors of functioning, like a wire breaking, a mechanical fault, which isn't relevant to the abstract idea of the machine, and errors of conclusion, like, say, typing out a false statement or getting a sum wrong. A machine can absolutely make those kinds of errors.
And what about thinking about itself? Self-reflection.
He addresses that too. Can a machine be the subject of its own thought? He concludes, yes, it can. For instance, by examining its own programs, maybe debugging itself, or predicting changes in its own structure based on inputs, that's a form of self-reference.
Okay, so he's systematically knocking down these disabilities.
Yeah.
Then there's the really famous one, Lady Lovelace's objection. Stemming from Babbage's earlier work, the idea that machines can only do what we tell them to do.
Right. The originality problem.
Yeah, that feels like a big one. No real creativity, just execution. How did Turing tackle that way back then?
It's a great point. Lady Lovelace, observing Babbage's analytical engine, a mechanical precursor to computers, stated it had no pretensions to originate anything. It could only follow instructions.
And Turing.
Turing actually agrees. He says, yes, that was true of Babbage's specific machine. But, crucially, he argues, that doesn't mean future, more advanced machines couldn't originate things.
Okay, so don't generalize from the past.
Exactly. And what's really fascinating is how he handles a variation of this. The idea that a machine can never take us by surprise.
Because if we programmed it, we should know what it'll do.
That's the intuition. But Turing quite charmingly admits that machines surprise him frequently. Often, he says, it's because of his own rushed calculations or because he forgot some initial assumption he fed into it.
So the surprise comes from human limitations, not machine magic.
Partly, yes. But he also suggests that appreciating something as surprising requires a creative mental act in itself, whether the surprising thing came from a human or a machine. It challenges this fallacy that just because something is a logical consequence of its premises, we instantly see that consequence.
Ah, I see. So a machine could derive something complex from its programming that we didn't explicitly foresee, even though it followed the rules, and that would feel like a surprise, like originality.
Precisely. It anticipates this idea of emergent behavior, where complex results arise from simple rules in ways that aren't immediately obvious, even unintended consequences. It's remarkably forward-thinking.
It really is incredible how he just dismantled these arguments, often by just, well, expanding our definitions or questioning our assumptions. So, okay, the game is set. The machine is defined as a universal digital computer. The main objections are addressed. How did Turing actually envision building a machine that could pass this test? He points towards learning machines, doesn't he?
He does, yes. He basically says, look, the real challenge isn't building the hardware, the engineering. The main problem is programming.
Software, essentially.
Right. And he believed that if you could program a computer with enough storage, he threw out a figure like 109 digits, maybe 1 billion bits or bytes.
Which he compared to.
He compared it to the information content of the entire Encyclopedia Britannica, or maybe a fraction of the brain's estimated capacity. He felt that scale of storage, combined with the right program, would be enough for it to play the imitation game reasonably well.
Okay, so big memory, clever program. But how do you write that program?
Well, rather than trying to program an entire adult mind from scratch with all its ingrained knowledge and complexities...
Which seems impossibly hard.
Right. He proposes something much more visionary. Simulate a child machine.
A child machine?
Yeah, think of it as a more blank slate. His words were something like, little mechanism and lots of blank sheets. And this child machine could then be educated, taught over time.
Wow. So machine learning, basically, back in 1950.
Absolutely. I mean, this concept is just one of his most profound insights. He recognized, decades ahead of his time, that learning from data, learning from experience was going to be far more powerful and feasible than trying to explicitly code every single rule of intelligent behavior.
That's the foundation of modern AI right there.
It really is. Neural networks, deep learning, it all comes back to this core idea of machines that learn.
That's such a powerful analogy, comparing it to raising a child. But, I mean, how far does that analogy go? How would this teaching actually work It can't be exactly like human education, can it?
Well, he breaks down human development into sort of three parts: the initial state you're born with, the education you receive, and then all the other experiences you have.
Okay.
So the child machine would undergo an education process. You'd experiment with it, you'd observe its responses, see how well it learns, much like a teacher interacts with a student.
Trying things out, seeing what works.
Exactly. And he even draws this really interesting parallel to biological evolution. He sees the child machine's initial structure, its basic program, as like hereditary material.
The genes, sort of.
Kinda. And
Yeah.
then changes made to its program during learning are like mutations. And the judgment of the experimenter deciding if a response was good or bad acts like natural selection.
Guiding the development.
Right. And this process could definitely involve punishments and rewards to guide behavior, which sounds a lot like reinforcement learning today. Though he also noted that using unemotional communication channels would probably be vital for teaching complex things to avoid human emotional biases creeping in too much.
That's fascinating. And he also touches on the idea that we might not fully understand how it's learning, right?
Yep.
The black box idea.
Yes, that's another incredibly prescient point. He acknowledges that a teacher might be largely ignorant of quite what is going on inside the learning machine.
Which is exactly what we say about complex neural nets today.
Exactly. Unlike traditional programming where you want to understand every single step the machine takes, with these learning machines, their internal workings might just become too complex for us to fully grasp. They develop their own internal representations.
And he saw that as, okay, maybe even necessary.
He seemed to view it as a natural consequence. He even suggested this human fallibility. The machine not being 100% certain or predictable might be a feature, not a bug. Because if a learned process always gave a guaranteed result, he argued, it couldn't be unlearned or adapted when circumstances change. That flexibility, that ability to revise, is key to real learning.
And did you think randomness played a role in this learning? That seems counterintuitive for a deterministic machine.
He absolutely did. He suggested including a random element in a learning machine,
Why?
especially when it's searching for solutions to problems or exploring new ways of behaving. He compared using this random method to evolution itself. He argued it can actually be more effective than a purely systematic step-by-step search, especially when there might be many different good enough solutions, or when the space of possibilities is just too vast to explore completely.
Like stumbling upon a good idea by chance sometimes.
Pretty much. It's foundational to many modern optimization techniques that use randomness. And then he concludes by kind of pondering, okay, where should we start with this huge project? Should we focus on abstract activities first, like teaching a machine to play chess?
Symbolic AI.
Right. Or should we go the other route? Give machines sensory organs, eyes, ears, and try to teach them language and how to interact with the physical world, more like how a child learns.
Embodied AI.
Exactly. And his conclusion, he basically says we should try both, which again just shows the amazing breadth of his vision. He anticipated these major, sometimes competing approaches in AI decades before they really took shape.
What an incredible journey into the mind of, well, a true visionary. It's amazing. From a simple parlor game, really, to grappling with the fundamental nature of intelligence itself. Turing laid the groundwork for practically everything we're seeing and experiencing with AI today.
From large language models to self-driving cars, yeah.
It's just absolutely remarkable how many of his ideas, his conjectures, as he modestly called them, have turned out to be foundational truths. They shaped research and development long, long before the technology caught up.
Indeed. His paper didn't just redefine the question of machine intelligence, moving it from philosophy to something empirically testable. It also basically outlined a roadmap for how you might build that intelligence.
A roadmap we're still following.
In many ways, yes. Learning machines, the universal computer concept, the focus on behavioral output rather than inner states, these are still the pillars of modern AI. And, he closed his paper with a simple yet really profound sentence. He said, we can only see a short distance ahead, but we can see plenty there that needs to be done.
Still true today.
Just as true now as it was in 1950. That spirit of relentless exploration, knowing there's so much more to figure out, it's still driving the field.
So, after exploring Turing's brilliant foresight, it leaves you thinking, doesn't it? If you were the interrogator in Turing's game today, right now, do you honestly think you could tell the difference between a top-tier AI and a human?
It's getting harder, isn't it?
It really is. And what does that realization mean for how you define thinking in this age? An age where machines can generate poetry, hold surprisingly deep conversations, and yes, even surprise us. Something to ponder.